Hello. So in the previous class, we had ended with a discussion about conservative systems. So we had seen that the centers in conservative systems end up being robust fixed points, unlike those in non-conservative systems where the center could be easily changed into an unstable or a stable spiral by the influence of the nonlinear terms. So today we'll continue over from that. So here's a theorem that actually says why the nonlinear centers are stable. So the theorem is as follows. So suppose we have the 2D nonlinear system or the conservative system rather, which is this. And suppose that f is continuously differentiable. Now let there be a quantity which can be defined as e of x. So this is a conserved quantity. So we had seen that by a conserved quantity, we mean that this quantity does not change along the trajectories. And suppose that x star is an isolated fixed point of the system. By isolated fixed points, we mean that there are no fixed points in a small neighborhood surrounding this fixed point x star. So if all these conditions are satisfied, and if the fixed point x star corresponds to a local minimum of E, then all the trajectories which are close to this fixed point x star are closed trajectories. So this theorem basically states that if in a conservative system there is an isolated fixed point, that means there are no other fixed points in its neighborhood, then all the trajectories which are sufficiently close to that fixed point will end up being closed orbits. So this is something which we had seen earlier when we had studied the case of the double well potential. We had seen that there were three fixed points. One was a saddle and the other two were centers. And the trajectories which were sufficiently close to the center were closed trajectories. And they also ended up being the minima of the potential, or where the conserved quantity was at a minimum. So this theorem shows that nonlinear centers are in fact stable when the system is conservative. Now let us take a look at another type of system, which are known as reversible systems. So the reversible systems are the ones which obey a time reversal symmetry. By time reversal symmetry, I mean that if you change the time t to minus t, then the solution remains the same. That means the system remains unchanged. An example of a system that obeys time reversal symmetry is like this: x dot equal to y and y dot equal to n, a function of x, where what is y? Y is the velocity. So under time reversal, you know that if t goes to minus t, then y goes to minus 5. So if you make this change of variables, you will see that this system, and plug this into this equation, you would see that the system will remain unchanged, right? So this basically means that every trajectory has a twin. So every trajectory and the other twin, and they differ from each other by a reflection in the x-axis. So for example, if you have a trajectory going forward in time like this, so this is for t going to infinity, you would have a similar trajectory going backwards in time like this, which is a mirror image of this symmetry about the x-axis. So this is t going to minus infinity. And this is what underlines a reversible system. So in general, any system is invariant under the transformation going to minus t and y going to minus y if it has a form that f is in y and g is even in y. So this basically means that f of space. Okay. So this system is an example of a reversible system under the transformation that t goes to minus t and y goes to minus y. So the theorem which we had shown for the nonlinear centers to be stable for conservative system, the similar theorem also applies to reversible systems. That means suppose we have a reversible system like this, then sufficiently close to the origin, all the trajectories will be closed curves. That means for such a system, the origin will be a fixed points and all the trajectories which are sufficiently close to the origin will be centers. So let us take a look at an example of such a system. An example can be written as x equal to I minus y cube is y dot equal to minus x minus y square. This is the g of xy. So you see that g of xy is given with respect to y while f of xy is odd. So now the fixed points of the system are basically given by the equation that 1 minus y square equal to 0, which implies that y is equal to 0 and plus minus 1 and x equal to minus y square. So the fixed points would basically be 0, 0, plus 1, 1, plus 1, minus 1. So these are the three fixed points of the system. Now let us take a look at the Jacobian matrix A. So the matrix A is basically given by del f del x is 0, del f del y is 1 minus 3y square, del g del x is minus 1, del g del y is minus 2y. Okay, so at the fixed point 0, comma 0, we have a is equal to 0, 1, minus 1, 0. Right, so the trace is 0, determinant is equal to plus 1, so the origin is a center. It is a nonlinear center. And because the system is reversible under the transformation that t goes to minus t and y goes to minus y, so the origin ends up being a robust fixed point. That means the center is a robust one and all the trajectories which are sufficiently close to the origin would keep on going around it in circles. And the other fixed points so for the other fixed points, we have the determinant A to be equal to 0, -2, -1, and +(-2). So in this case, the trace is given by either +2 or -2, and the determinant is equal to -2. So since the determinant is negative, both these fixed points are saddle points. So what does the phase space look like over here? So the stable and unstable ideal directions can simply be computed if you calculate the, what do you call them, the eigenvectors. So this is x, y. So the origin is a center. There is a fixed point over here, which is a saddle, and the fixed point over here, which is another saddle. Okay. So if you do the computations of the eigenvectors, you will see that the stable eigendirection is somewhat like this, and the unstable eigendirection is somewhat like, and similarly for this one, the stable eigendirection is somewhat like this. The unstable one is something like this. And if you extend them, you will see that, so the unstable and the stable directions basically give us our direction of oscillation. So you see that there will be a clockwise oscillation around the origin like this. The trajectories end up looking somewhat like that. And then you have trajectories which go like that around the origin. And these trajectories can also be extended like this, and then they go away like that. So similarly, this trajectory can be extended in this way. And there are trajectories which come from there. Sorry. So like that. So trajectories which come from here, they simply go away like that. Trajectories coming from here go away like that. These trajectories also follow this particular path. And there are trajectories which start from here, which go like this, and then away like that. So you see that there are certain so this particular orbit is the most interesting one. So, and yesterday we had seen the example of a homoclinic orbit where the trajectory tries to return to its initial point as t goes to infinity. So as t goes to plus minus infinity, they come to the same point. That was a homoclinic orbit. So this here is an example of a heteroclinic orbit. So heteroclinic trajectories are basically those trajectories which connect a pair of saddle points. So you have two saddle points like this, and if they're connected by an orbit, which goes from here all the way up here. So this is an example of the heteroclinic orbit. They are also known as saddle connections. Okay, so now that this part is done, let us take a look at the example of a pendulum, which is perhaps the most simplest example of a conservative system, and yet it is highly complex to analyze in all its completeness. So we had seen that the equation for the pendulum is given by theta double dot plus g by L sine theta equal to 0. So this is basically the equation of a pendulum which hangs from the vertical direction like this. pendulum. This angle is known as theta. This is the length of the string. Okay, and the mass is m. So if you introduce the frequency omega equal to square root of g by L, and then you define a normalized timescale as tau equal to omega t, then we can rewrite the equation in terms of this non-dimensional timescale as theta double dot plus sine theta equal to 0, where theta double dot is the double derivative of theta with respect to tau. So the corresponding coupled first order systems is given by theta dot equal to v and v dot equal to minus sine theta, where v is the angular velocity of the pendulum and it's a dimensionless quantity. Now the fixed points of this equation are basically given by v equal to 0, star equal to 0, and sine theta star equal to 0, which implies that theta star should be equal to n times pi. So the fixed points are therefore given by n pi comma 0. Okay. Now to study the nature of the fixed points, what do? We again construct the Jacobian matrix. So A is equal to del f del theta is 0, del f del v is 1, del v del theta is equal to minus cos theta, del g del v is equal to 0. Okay. So when theta is equal to 0, so when theta is equal to 2n pi, that means it is an even multiple of pi, where n belongs to the set of all integers, then the matrix A becomes 0, 1, minus 1, 0. And as we saw earlier, this gives me a center. So all the centers are these fixed points basically. All right. And when theta is an odd multiple of pi, that means it's basically 1 plus 1 pi, then is equal to 0, 1, 1, 0. And therefore, all these points are saddle points. So they correspond to 1 plus 1 pi comma 0. So if we try to map the phase portrait, in this plane, so suppose we consider various multiples. So this is 0, pi, pi, and so on. Again, minus pi, 2 pi, minus 2 pi, and so on and so forth. Okay, so the origin is a center as we saw earlier. Points at minus pi and plus pi are basically saddle points, and they have the same eigendirections. So the eigendirections we had calculated previously are the unstable eigendirection is the 1, 1 direction, and the stable eigendirection is the minus 1, minus 1 direction. So this is the stable direction. And similarly for this point, also you have the 1, 1 direction to the unstable direction, and the stable direction is the minus 1, minus 1 direction. And the origin is a center, so the direction of The saddle orbits should tell you what the circulation about the center should be like. So it will go like that, and it will be a clockwise circulation like this. Okay. So the arrow will point this way. All right, and these will be the homoclinic orbits that we had seen before. Sorry, this will be the heteroclinic orbits instead of the homoclinic orbits because they are connecting two saddles. Similarly, here also you will have clockwise oscillations like this, which grow in size till they are finally connected by the homoclinic heteroclinic orbits, which are in this direction. And here also there will be these clockwise oscillations. And then you will have heteroclinic orbits, which go like that over here. So this gives me the complete picture of the phase portrait of the system in the theta v plane. Now let us take a look at what the energy of the system should be. So first of all, you see that there are heteroclinic orbits here. And if you do the transformation that t goes to minus t and v goes to minus v, then you will see that this equation remains unchanged. So in fact, this is not only a conservative system, but also a reversible system. Now, why do I call it a conservative system? So the physical intuition is that there is no damping term in this equation. And moreover, if you multiply the equation theta double dot plus sine theta equal to 0 by the term theta dot, and then you integrate over time, what you get is that of theta dot square minus cos theta is a constant. So you can basically define a constant of this form E such that the E is constant over all trajectories, right? So that is why this is a conservative system. So the energy function E as a function of theta and V can be written as E squared by 2, which is the physical interpretation of the kinetic energy, minus cos theta, whose physical interpretation is the potential energy. So for the orbits to be approximately circular, we should have theta square plus v square to be a constant. All right. So sufficiently close to the origin, you can take theta to be very small, and then you will see that in fact cos theta turns out to be equal to minus theta square, and then you get a, if you do the Taylor series expansion of cos theta, you would get 1 minus some theta squared term, and then you take the 1 to the other side, so you will get theta squared plus v squared to be a constant. So that says that the origin, which has trajectories which are sufficiently close to the fixed points or the origin, should be in fact circular orbits. Now from here one can also map the orbits which correspond, the energies of these orbits which correspond to these heteroclinic trajectories. So the heteroclinic trajectories are those trajectories which just about stop oscillating, going around in circles about the origin. So beyond, if you take energy to certain values which are beyond a particular value, you will see that the cos theta terms becomes imaginary, and those cos theta term will basically disappear, and those trajectories will cease to oscillate. So since cos theta should be less or equal to 1, equal to square by 2 minus cos theta is equal to square by 2 minus e. So basically, e should be such that e squared by 2 minus e should be less than 1. So if you put, say, v equal to 0, then you see that the threshold is e equal to 1. For e greater than 1, the pendulum will whirl around the top. Okay. Now, if you introduce a bit of damping into the system, you would find that the nonlinear center would eventually end up becoming a spiral. Okay, and the trajectories will converge towards the origin. So that will change the stability of the fixed points. Now we move to another example of a phase plane analysis. So here we study population dynamics. So basically, we begin with the famous model of population dynamics, which is known as the Kotka-Volterra model. Okay, so suppose here we have two species, both are herbivorous species which don't each other. So one is rabbits and the other species are sheeps. Now both of them, they compete for the same food, which is grass. Okay, and the amount of grass is limited. So what happens? There is a competition between species. So they would all try to feed off the same grass. And in this model, we neglect the effects of other complications like predators, seasonal effects, and influence of other factors on sources of food, and so on and so forth. So we make the following two main effects that we consider are as follows. One is that both the species grow to their carrying capacities in the absence of the other. So one is that both of them are assumed to follow this logistic growth pattern, which we had studied earlier. Okay, and because physically speaking, rabbits have the ability to reproduce faster, so we say that the growth rate of the rabbits is faster than the growth rate of the sheep. So this is one assumption that we make. And the second assumption is that when the rabbit and sheep encounter each other, then there is competition. So we assume that the conflicts between rabbit and sheep occur at a rate which is proportional to the size of each population. And in that competition, one can be affected more than the other. So we assume that the effect of the conflicts is more severe for the rabbits. In other words, the conflicts tend to reduce the growth rate of the rabbits faster than it reduces the growth rate of the sheep. So one specific model that incorporates these assumptions is that x dot equal to x into 3 minus x. This is the logistic growth part, minus 2xy, and y dot equal to y into 2 minus y minus xy. So as you can see over here, x represents the rabbit population at any time t, and y represents the sheep population. So the growth rate of the rabbits is faster than sheep. That's why you have the factor of 3 over here and the factor of 2 over here. Okay, so the first task is to find out the fixed points of the system. So the fixed points which we obtain are given by x dot and y dot equal to 0, and then they turn out to be 0, 0, um, 0, 2, 3, 0, and 1, 1. So basically, these fixed points represent the stable values of the population. So you see that one fixed point will say that there are no rabbit and sheep at all. One fixed point says that there will only be sheep. This one says that there will only be rabbits, and this one says that both will be there in equal quantities. So the next thing that we do is that we calculate to classify the fixed points. We calculate the Jacobian matrix. So this is basically given by del f del x, which turns out to be 3 minus 2x minus 2y. Del f del y is minus 2x. Del g del x is minus y. And del g del y is 2 minus y squared minus, so 2 minus 2y minus x. Okay. So now we consider each of the four fixed points turn by turn. So first you consider the fixed point 0 by 0. For that we see that matrix A becomes 3, 0, 0, 2. So the trace is 5, determinant is 6. So t square minus 4 delta is greater than 0, and therefore this turns out to be an unstable node. All right. So we see that there are two eigenvalues of the matrix corresponding to lambda equal to 3 and 2. Lambda equal to 2 is the slower eigendirection, and the eigenvector corresponding to lambda equal to 2 is basically 0, 1. So the slower eigendirection is the y-axis, and the trajectories close to the origin will be parallel to the y-axis. So the phase portrait near the origin, which is an unstable fixed point, will look somewhat like this. Mind you, x and y can only take positive values, so this is what the trajectories close to the origin will look like. Similarly, for the fixed point 0, 2, which says that there will be only be sheep and no rabbit, the matrix A is given by minus 1, 0, minus 2, 2 minus 2 is 2 minus 4 is minus 2 again. So for this again, the eigenvalues lambda are equal to minus 1 and minus 2, which shows that this is a stable fixed point. And the slower eigendirection corresponds to lambda equal to minus 1. This has the eigenvector of 1 minus 2. So basically the flow close to this fixed point, this fixed point will be somewhere over here, and the slow eigendirection will point somewhat in this way, and the trajectories will all be parallel to this. So you know, it's like that. All right. The third fixed point is given by 0, 3. Sorry, it will be 3, 0. For this, the matrix becomes minus 6, 0, minus 1. Here again, lambda equal to minus 1 is that it's a stable node, and the eigenvector corresponding to the smaller eigenvalue is minus 1. So this fixed point will remain somewhere over here. This is the stable eigendirection, and all the trajectories will try to become parallel to this. And finally, the last fixed point, which is 1, 1. For this, you have A equal to -1, -2, -1, -1. So this matrix basically has the trace to be equal to -2 and delta equal to -1. So since delta is -1, this is a saddle fixed point. So the phase portrait near the saddle fixed point, which lies at 1, 1 over here. Thus, stable eigendirection is this one, and the unstable eigendirection turns out to be this because the eigenvalues are equal and opposite. Therefore, the stable and unstable eigenvectors you could occur at right angles. So if you combine all of the four cases, then the phase space will look like this. So here, this is an unstable fixed point. The trajectories tend to go outwards from here like that. Okay. And you have a stable fixed point, saddle point at 1, 1. Here you have this one to be the stable manifold. And this is the unstable manifold. There is a fixed point which is at 2, 0, which is the stable fixed point. Here, this was my direction. There was one fixed point which was here, 3, 0. This is the direction corresponding to that. And the refugees will approach this. So if you now end up joining all these trajectories, the whole phase portrait, it will look somewhat like this. So any trajectory would start from here, you will go like this. Yeah. So this is what the trajectories will look like. This corresponds to the stable manifold. Okay, so basically my y represents the sheep, so we call this the sheep axis, and this is the rabbit axis. So this basically tells us that if we start off from below the stable manifold at a very small population, in other words, if you start off with a smaller population of sheep and a larger population of rabbits, then the population of rabbit tends to dominate at the end. Whereas if you start off with a larger population of sheep just above the stable manifold and smaller population of rabbit, then the sheep population will end up dominating. Okay, so it all depends on where you start with respect to the stable manifold. And so in this sense, we can actually define what are known as basins of attraction. So all these places over here in the stable manifold, which lie to the right of the stable manifold, all these fixed points over here, they form the basin of attraction for the rapid population. So all the points to the right of the stable manifold form the basin of attraction for rabbits. So this is over here. And all these points which lie just above the stable manifold or to its left, they form the basin of attraction for the sheep. Right. So basin of attraction basically means that all the points which start off in a given location, a given initial condition which lies in the basin of attraction of a fixed point will end up reaching that particular fixed point in the limit of long time. And the stable manifold basically forms the basin boundary separating the two basins of attraction. Okay, so that tells us about the examples of a rabbit sheep population. You can also have a conservative population model, or in other words, a conservative system which models population dynamics, and it will look somewhat like this. So this is also what is called a predator model. So in the previous example, we did not have a predator. Now we have a predator. Okay. So suppose there are two species R, which represents rabbits, and F, which represents foxes. So the foxes basically feed on rabbits, and a simple model for the dynamics is given by AR minus ERF and F dot equal to minus F plus TRF. Okay, so this basically states that A is the intrinsic growth rate of rabbits. So in the absence of foxes, F will be 0, and the rabbits will are assumed to grow exponentially here instead of the logistic growth which we had earlier. E is the rate at which the foxes prey on the rabbits. So it is the death rate of the rabbits due to predation by the foxes. Similarly, D is also the rate at which the foxes population could start growing once they start consuming the rabbits. And C represents the intrinsic death rate of foxes. And multiplying this by F implies that the foxes die if the rabbits are less in number. So if rabbits are less in number, the food for foxes also decreases, and then they end up starving and dying. So this is a very simple preparator model, and moreover, this is not physical in many regards, but nonetheless, it forms a simple model for studying preparator dynamics. So we assume that the model parameters A, B, C, and D are all greater than 0. And because this is a conservative model, we can also find the conserved quantities. All right. So how can you find the conserved quantities? So you remember Hamilton's equation of motion, Hamiltonian equation. So in terms of the Hamiltonians, equations, the Hamiltonian of the system, then we can write that del H by del Q is equal to minus P dot and Q dot equal to del H by del P. So basically the invariant over here is the H. So you can also use the same tactic to find this. So suppose we denote Q as R and P as F, then we can write R dot is equal to some del H by del F. Or you have to increase the R equation with respect to F. So we add so this is partial integration with respect to f. So it's a r f plus some constant c1, and then you also have um, dot equal to. So you have these two equations for f, and you have the constants. So basically, if you find the constants with the correct initial conditions, then you can substitute for them and obtain the final value of h. So in this way, you can also define a conserved quantity. And so once you do that, that's a different thing. But now you can also analyze the dynamics of the system. So the first thing is that we have to find the fixed points of the system. The fixed points are given by the solutions of. Okay. Now the constraint was that a and b are both greater than 0. So if a and b are both greater than 0 and the population has to be greater than 0, so this quantity is greater than 0. Therefore, we have r equal to 0 to be a fixed point, and corresponding to r equal to 0, the other fixed point will be f equal to 0. So the origin is the fixed point. So fp is basically r star comma f star, and this is 0 comma 0. So the Jacobian matrix can be written as E equal to um, L, L R is B plus BF R del G del S del G del R will give me F minus C plus ER. Now, if you evaluate this at the origin, that is 0 comma 0, and we end up getting A 0 0 minus C. So therefore, my trace is now A minus C. Determinant is equal to minus AC, and my what do you call that? Trace squared minus O delta equal to A minus C whole squared minus plus O AC is equal to A squared plus C squared plus 2 AC. So since A and C are both greater than 0, this basically means that this is always greater than 0. Therefore, the origin can not be a spiral. Okay. So the determinant is basically greater than 0. And now if the trace is equal to 0, that means if A is equal to C, then this basically means, oh, hold on. So the determinant is always less than 0, right? So this basically implies that the origin is a saddle point, right? Therefore, the fixed point at the origin is a saddle. And as we saw from our analysis that the origin in fact is the only stable fixed point unless both A and B are 0. So that solves the reversible, that solves a related problem. Now we move on to a new topic in two-dimensional systems, which is the concept of limit cycles. So we had seen that oscillatory solutions are possible if the origin is a center, then the solutions will continue to oscillate in closed orbits. And if it was a spiral, the oscillations will decrease or increase with time amplitude. But we had not seen a closed orbit that attracts the nearby orbits. So if the origin is a center, then the orbits are basically fixed point is a neutrally stable one, and the closed orbits are not attracting, neither repelling, and the amplitudes are usually determined by the initial conditions. So the limit cycle differs from a center in the sense that it can be an attracting or a repelling closed orbit. So by attracting or repelling, I mean that it can be a stable limit cycle or an unstable limit cycle. For example, if you have a cycle like this, any trajectory starting from inside approaches it, any trajectory starting from outside also approaches the cycle. This one is an example of a stable limit cycle. It can also be an unstable limit cycle if any trajectory starting from it goes up to infinity, while any trajectory starting from its inside spirals down with center. Or it can be, this is an example of an unstable limit cycle. Or it can also be a half stable limit cycle. Okay. So suppose the dotted line is a limit cycle. Half stable generally means that so I was what I was saying, the half stable limit cycle basically means if you have a cycle like this, then the trajectory starting from its inside can spiral down, while that starting from outside can approach it like this. So this is an example of what the other way around. That means the trajectory starting from inside can approach it, while the one starting from outside can leave it entirely. So this is what is called a half stable limit cycle. And one more important thing is that centers depend upon the initial condition. right? Because it depends on where you initially start from. A limit cycle is basically an attractor of the system. So it is basically approached by the system as time goes to infinity, or it is the trajectories get repelled away from it, and therefore it is independent of the initial conditions. So in these two respects, it differs from a nonlinear center. So here is a prototypical example of a simple limit cycle. So suppose you consider the system in the plane polar coordinates as r into 1 minus r squared theta dot equal to 1. So the fixed points of this system, they correspond to r star taking the values of 0 and 1. Since r cannot be negative, we only choose the positive value of 1. And you would find that if you the fixed point corresponding to r equal to 1 is a stable one, and the one corresponding to r equal to 0 is the unstable one. Because this simply follows from the one-dimensional analysis which we had done. F of r looks like this. So the flow approach is this. Right. So this is stable and this is unstable. So if you look at the phase portrait of such a system, then you will see that this one is the unstable fixed point, and the one corresponding to the radius circle corresponding to the radius of one circle. Yeah, this is the stable fixed point. And since theta dot equal to plus 1, so all the trajectories, they oscillate in the anti-clockwise direction. So what happens is that a trajectory close to the origin, it starts up like this, and then it approaches the limit cycle. So the limit cycle is basically given by the circle of radius r equal to 1. Similarly, any trajectory which starts from outside will approach it like this. Those trajectories starting from here will come like this, and so on and so forth. R equal to 1. And this is drawn in the xy plane. So you see that we get a stable limit cycle having a radius r equal to 1. And if you try to plot a time series of, suppose this one which comes from a large value of x, then the time series would look somewhat like this. So it comes, this is x equal to 1, it comes from this large value, and then it starts oscillating about this. So this amplitude corresponds to x equal to 1. And this is -1. So that is what a time series of such a system will look like. Now, another interesting thing which will come in the next class is a bifurcation of a limit cycle. So instead of 1, if you had a variable parameter a in this equation, then you would see that there will be a saddle node bifurcation where the two fixed points will disappear. So that basically corresponds to the disappearance of a limit cycle. Okay, a limit cycle can appear and disappear by saddle node bifurcations, and also we'll see in next class certain Hopf bifurcations which can change the stability of the limit cycle, but that's a different topic. So I'll take a break of a few minutes. After that, we'll see how one can characterize limit cycles, how one can justify the existence or the non-existence of limit cycles in typical nonlinear systems. Okay, so starting off from where we had left off. So the first theorem, which rules out closed orbits, is as follows. So there can be systems which are known as gradient systems. By gradient systems, I mean that the x dot, it can be written as some gradient of a potential or some scalar field given by v of x. So such a system is called a gradient systems, and the theorem is that closed orbits are impossible in a gradient system. Okay, why? So we can prove this by contradiction. So suppose that there was a closed orbit in a gradient system. So if there was a closed orbit, then basically it means that a trajectory will return to its starting point after completing one oscillation. And so the net change in potential, since v is only a function of x, delta v will be zero after full oscillation, right? So if there exists a trajectory along which delta v is equal to zero upon completing an entire orbit, then there would be a closed orbit in that system that will correspond to a closed orbit. So this quantity delta v, it can be written as, suppose we take a time zero capital T to complete one oscillation. So basically this is given by dv dt of t. And since we can write by chain rule that this is nothing but gradient v into x dot dt. Right. Now gradient v was nothing but x dot. So this is nothing but minus of 0 to t mod of x dot square dt. Now since this is a positive definite quantity, this means that delta v is always greater than 0. So for such systems, for gradient systems, the change in the potential along any trajectory is always less than 0. And this basically implies that not equal to 0 means that it will never be a closed orbit. So we prove by contradiction that the gradient systems can never have a closed orbit. And in gradient system, there's always a stable fixed point and the system always tends towards that stable fixed point. So the important thing about a gradient system is that any dynamical system is not a gradient system. It is a gradient system only if it can be written as x dot equal to minus of gradient v. So for example, consider this system that x dot equal to sine of y, y dot equal to x cos y. Now, let us see if it is possible to write this in terms of a gradient system. All right. So we saw that the gradient system had x dot equal to minus grad v, which basically implies that x equal to minus del v del x and y dot equal to minus del v del y. So basically v will be given by integration of x dot with respect to dx, which in this case basically gives me x sine y plus some constant c1, and it can also be written as uh, also written as minus of dy, which again turns out to be minus x sine y plus some constant c2. So choosing c1 equal to c2, we have the potential can be written as minus x sine y. So you see that this system, it is an example of a gradient system, and as a result of that, it cannot have any closed orbits. So another criteria which can help us in ruling out closed orbits are what are called Lyapunov functions. So what is a Lyapunov function? Lyapunov function, suppose you have the system as x dot equal to f of x, with x star being a fixed point of the system, then a Lyapunov function is defined as v of x. If v of x is a Lyapunov function, then v of x has to be continuously differentiable with the following properties: that one, v of x will be greater than 0 for every x which is not the fixed point, and v at x star should be equal to 0. So v has to be positive definite. And the second criteria is that dv dt should be less than 0 for all x not equal to x star. In other words, the dv dx, this will actually be gradient of v, not dv dt. So gradient of v along any particular direction should always be negative. In other words, all the trajectories should look as if they converge towards the fixed point. So if we are able to define a Lyapunov function for a particular system, then there would one can be sure that there cannot be any closed orbit in that system. But the problem is that it is very difficult to define Lyapunov. There is no systematic way of constructing Lyapunov functions for systems. So the earlier method which we saw was a better method of ruling out closed orbits than this method of Lyapunov functions. Okay, now let us take a look at a theorem which states the opposite. Now we had already seen that what in which ways we can rule out closed orbits, and now we will see a theorem which states the conditions under which a 2D system can have a closed orbit or a limit cycle. So this is called the Poincare-Bendixson theorem. So the theorem is as follows. Suppose you have this large region of the phase space, this curve bounding the region R, and you have a smaller region at the inside. Okay, and this encloses a point P. Okay, so the region between the inner circle and the outer circle is what we called R. Now, what does the theorem say? That suppose number one, R is a closed bounded subset of the plane, and number two, x dot equal to fx has no fixed points in R, and x dot equal to fx is also a continuously differentiable variable vector field on this open set of R. Number three, there exists a trajectory C which is confined in R. That means is confined in R means that it starts in R at t equal to 0 and stays in R till time equal to infinity. So if these three conditions are satisfied, then C is either a closed orbit by itself or it spirals towards a closed orbit in R as t goes to infinity. In other words, R contains a closed orbit. So this is the statement of the Poincare-Bendixson theorem, which states that if these 3 points are satisfied, then R will contain a closed orbit. So if you take a look at this region, then the region between the inner and outer circle is R if there are no fixed points. And if there exists a random trajectory over here, which we call this trajectory as C, then it will always approach this closed orbit, which we show by the dotted line over here. So this states this is what states that if these conditions are satisfied, then there will always be a limit cycle inside R. So this is the criteria for the existence of a limit cycle. So from this criteria, how can one be so sure that a trajectory C always exists? So for the existence of such a trajectory, such a closed orbit, one is that there cannot be any fixed points in that region, and that is something which we can find by linear stability analysis. The other more tricky part is the existence of a trapping region. So for a closed orbit to exist inside R, R has to be a trapping region. In other words, if you have a larger boundary like this and a smaller boundary like this, then the vector field should be such that it points inwards at this larger boundary, and along this smaller perimeter, it points outwards. So you see, it is as if all the trajectories which start in this in-between region, it's as if they remain trapped in this in-between region because of the vector fields on the boundary. So this is how one can define a trapping region. So a characteristic of a trapping region is that the vector field on its outer boundary will point inwards and the vector field at every point on its inner boundary will point outwards. And that's what defines a trapping region. Now here we start off with an example to see whether a limit cycle can exist or not by constructing a trapping region or from the Poincare-Bendixson theorem. So as an example, we consider um, this system, which is written as r dot equal to r square plus mu r plus theta, and theta dot equal to 1. So uh, when mu is equal to 0, we saw an earlier example that there is a limit cycle exists whose radius r is equal to 1. Right. Now let us see what happens when mu is not 0. When mu is greater than 0 basically. So to construct a trapping region, we need to find two quantities. One is r min and r max, which end up becoming the boundaries of the trapping region. So the annulus defined such that This is what will define the trapping region. So the one criteria is that there should not be any fixed points in this region. Hence, if such a region can be found, then the Poincare-Bendixson theorem will imply the existence of a closed orbit. So to find the lower bound, we require that R is greater than or equal to R main, right? And over here, R dot should be greater than 0. So R dot greater than 0 basically implies that the flow is outwards and the boundary. So this means that 1 minus R squared minus plus mu R cos theta is greater than 0. Now because cos theta is always greater than or equal to minus 1, so a sufficient condition for its existence is that 1 minus R squared minus mu R is, minus mu is greater than 0, which basically implies that R should be less than root over 1 minus mu. So in other words, R min should be less than root over 1 minus mu. And similarly for the outer boundary, we should have R less than R max, and at the outer boundary R dot should be less than 0. And because cos theta's maximum value is equal to 1, this basically implies that R max should be less than root over 1 plus mu. So we can construct a this will be R max should be greater than 1 plus mu. So we can construct a trapping region as an annulus whose outer boundary is R max and whose inner boundary is R min, and all the trajectories which start from within that particular annulus will approach the limit cycle, right? So therefore, by the Poincare-Bendixson theorem, and you see that the annulus will exist only when this quantity is real. In other words, mu has to be less than 1. So when this condition is satisfied, then closed orbits exist. Okay, so we will do another bigger example of the Poincare-Bendixson theorem in the upcoming class. But before that, we would like to see another important result of this theorem. So the Poincare-Bendixson theorem basically states that there cannot be any chaos in a 2D system, because the only oscillatory solution ends up being a limit cycle. On the other hand, in three-dimensional systems, there can be chaotic system. For example, in three-dimensional system, the trapping region will correspond to a area which is correspond to basically a volume which is enclosed by two shells. That shells can be spherical or non-spherical, and within that volume, the trajectories can wander about here and there in different directions, and they need not correspond to a limit cycle. So they can give rise to objects what are known as strange attractors, and on a strange attractor, certain changes in initial conditions can lead the trajectory to occupy different positions on that attractor. So that is the hallmark of chaos, right? So chaos can be possible only if the system is three-dimensional or higher. So next we come to what are called Leonard systems. So a Leonard system is the generic system of this form: x double dot plus f of x dot plus g of x equal to 0, where in general f and g can be nonlinear functions. So basically, Leonard systems are systems modeling nonlinear oscillators whose damping can be nonlinear and the restoring force can also be nonlinear. So one example of a linear system is the very famous van der Pol oscillator. So van der Pol oscillator is an example of a classic nonlinear oscillator which has been used for modeling various types of nonlinear oscillating circuits. They have been also used in biophysics for modeling the firing patterns of neurons and so on and so forth. So the van der Pol oscillator is basically given by the equation x double dot plus mu into x square minus 1 x dot plus x equal to 0. So this is f of x and this is g of x for the van der Pol oscillator. Okay, now the Leonard systems can be written in terms of two first order differential equations. So x dot equal to y and y dot equal to minus g of x minus f of x into y. So there exists a theorem called the Leonard theorem, which justifies the existence of a limit cycle in Leonard systems. So this theorem, called the Leonard's theorem, is as follows. So suppose f and g satisfy the following. One is that f and g are continuously differentiable for all x to g is odd function of x. 3 is that g is greater than 0 for x greater than 0. 4 is that f is even function of x. 5 is that f of x equal to 0 to x. If you du, basically the integral of f is odd. And a has exactly one positive 0 at x equal to a. B is less than 0 for 0 less than x less than a, and C is non-decreasing for x greater than a and approaches infinity as X goes to infinity. Lot of criteria. So if all these things are satisfied, only then I think I have lost all those criteria. Yeah, I think I've lost it. So if all those criteria are satisfied, only then will the system have a stable limit cycle. So you can look at the recording and read the criteria. So basically, that is what a linear theorem is all about. So basically, f of x, which was integral of fu du from x0 to x, this should basically have the form that this is x and this is capital F. It should be 0 over here, only one positive 0. It has to be positive and increasing over here, and here it can be anything. Okay, so if this is the case, oh, by the way, this has to be an odd function, right? So if it is an odd function, then whatever is on this side should be opposite to whatever is on the other side. Therefore, should look somewhat like this. Yeah, this you. This should be the form of capital F for there to be limit cycle oscillations. So first, let us take a look at the Van der Waals oscillator and see whether it has a stable limit cycle or not. So the Van der Waals oscillator equation was given by this. So f of x is equal to -1 minus 1, g of x is equal to x. So as you can see, this is odd, this criteria is satisfied, this is even, this is satisfied, g of x is greater than 0 for x greater than 0, so that condition is also satisfied. Finally, we take a look at the last condition, which is capital F of x. So the integral of f of u is given by mu into x is cubed by 3 minus x. All right. So this can be written as mu into x squared by 3 minus 1. And you see that it has a positive 0 at x equal to a equal to root over 3. So at root over 3, there is a positive 0. So this condition is also satisfied, and therefore the Van der Waals equation has a stable limit cycle. So now we will study the Van der Waals equation in more detail, not only because of its immense physical relevance, but also because of the way it can be used to study various kinds of nonlinear oscillations. So now we move on to what are known as relaxation oscillations. Okay, so what is known as a relaxation oscillation? So you see that there are certain types of oscillations where one phase of the oscillation is very slow. It seems as if the oscillator is kind of stressed over there. And as soon as it releases the stress, the remainder of the oscillation is completed in a very slow time scale. So relaxation oscillators are basically classified by two different time scales, a slow time scale and a fast time scale. And that is something that we will study, something that we will look at from the point of view of the Van der Pol oscillator. So let us consider the Van der Pol oscillator in the limit that the nonlinear damping term, that is mu, is much greater than 0. So we consider the limit that mu is very big, or mu is much greater than 1. So let us look at the phase portrait of the Van der Pol's equation in this limit. So in this limit, we can simplify the equation by dropping out the term which is linear in x, and then we get okay. Now this equation basically implies that we can write this as x dot equal to y and y dot equal to all right. This is not that helpful. Let us try some other method. So this equation can be written as ddt of all right. So we define quantities f of x equal to then this basically implies that ddt of zero. But it is not always correct to neglect this term. So basically, equation that so this implies that x2 plus u is equal to minus x. So now so if we define a quantity like that, then u dot equal to minus x, or in other words, the Van der Pol equation can be written in terms of the following coupled equations that is not equal to w minus mu and f, w dot equal to minus x. Now let us make one further change of variable that y is equal to w by mu. So we define a variable y in this particular manner. So in that case, the coupled equations turn out to be and now we try to analyze this system in the phase space of x and y. Okay, where y is defined in this manner. So y is basically plus f. Where f is given by this equation over here. So since we are only considering the limit of mu much greater than 1, so you see that when mu is, then first what we do is that we first look at the null lines of the system. So the null lines are given by the equation that x dot equal to 0 is be the x null line. So the x null line is basically given by y equal to fx, which is equal to x cubed by 3 minus x. And the other null line, that is the y dot equal to 0, it's called the y null line. This is basically given by the line x equal to 0. So if you try to map these things in the phase plane of x and y, then y equal to x cubed minus x line, it looks like this. And x dot equal to 0 line is basically the y-axis. So this is the line x dot equal to 0. And the y-axis is the line y dot equal to 0. This is x and this is y. So what would a typical trajectory look like if mu is much larger than 1? So let us suppose that we are starting off from somewhere over here. At this location of the phase space, you have the trajectory is basically lying above the y null plane. So basically here y is greater than f of x, and therefore x dot is positive. That means the flow should be towards the right. And what about the y dot part? The y dot part, because mu is dividing x over here, therefore y dot is almost equal to 0. So the flow which starts from this point, it goes to the right. Sorry, it goes to the right like this, and it approaches the y null plane. Now, as it approaches the x dot equal to 0 null plane, the x velocity decreases and becomes 0. So along this null plane, the flow goes vertically, tries to go vertically downwards. So the velocity is vertically downwards along this null plane over here. Okay. Why vertically downwards? Because y is minus x. So wherever there is minus x, the velocity will be vertically downwards like that. Anyway, And on this side, it will be vertically upwards on the left hand side where x is negative. So after it approaches this trajectory, it tries to go downwards. And as it moves away from the y null line, what happens is that the as it moves away from this null line, what happens is that y becomes less than f of x. So when that happens, x dot becomes negative and it tries to go left. But again, it tries to go right, and again, it tries to go left, and so on and so forth. There is a competition like that. So ultimately, what happens is that instead of wiggling around like that, this trajectory goes down along this y null line and it closely follows the null line like this. And once it reaches this point where the null line just starts to turn upwards, it moves far away from the y null line so that this quantity over here, it becomes substantially large. And since it is multiplied by mu, it becomes even larger. And so because it now lies below the y null line, y minus f of x is negative, and therefore the trajectory zaps to this left branch of the null line. Okay, so after it approaches the left branch of the null line, again it goes upwards because the velocity along the null line is positive vertically upwards, and it crawls along this null line like this, similar to what we had seen previously. And once it reaches the top, it again zaps back to this null line. And then it again starts this oscillation over again. So you see there is a large limit cycle which looks somewhat rectangular in shape and whose upper and lower limits are basically given by the maxima and minima of the y null line. And if you try to map it onto a phase, onto the time series of the variable x, that is the time series of the oscillator. So suppose you start off from some value of x over here, it increases very fast. Or rather, I should start from the origin of time because that is where I actually start. I start off from a positive value. It increases very fast. And then what happens is that there is a slow decrease like this. The slow decrease corresponds to this branch of the null line where it goes down. After the slow decrease, there is a fast decrease where it goes to the negative branch. And after the fast decrease, there is a slow increase like this, which is again followed by a fast increase so that it approaches the stable branch. Sorry, the amplitudes were wrong over here. Again, slow, fast, slow, fast, and so on. So you see there are alternating slow periods and fast periods followed by slow periods and fast periods. So this is time and this is x. So this is what relaxation oscillations actually look like. So we'll stop the lecture here today. In the upcoming class, we will see how one can quantify the timescale of the oscillation and how one can also study the system from the method of perturbations. Okay, so that's it for today.